Greetings to everyone. Our topic today will focus to pen tracing puzzle. Do you have any idea about pen tracing puzzle? Puzzles such as called pen tracing puzzle can be considered problems in graph theory. If we imagine a vertex placed wherever two lines met or cross over each other, then we have a graph. Our task is to start at a vertex and find a that traverses every edge of the graph without any repeating an edge. In other words, we need an Euler path, and an Euler circuit would work as well. Degree of a vertex. The degree or a valence of a vertex is the number of edges missing at the vertex. It is possible for a vertex to have a degree of 0 larger. We have degree of 0, degree of 1, degree of 2, degree of 3, degree of 4. Euler path is a path that travels through every edge of a graph once they start and ended at different vertices. Euler circuit is a circuit that travels through every edge of a graph once and only once they start and end at the same vertex. Discussing what an Euler path is compared that to Euler circuit, so take a look at this graph that we have here. These are the example of Euler paths that have degree of a vertex. So this example is even degree of 2, even degree of 2, even degree of 4, again with a degree of 4. This is odd with a degree of 3. Notice that we have 3 bridges connected to the vertex E, and the same applies with D. So this is a path and not a circuit for trial and error to find one such path. So this is one method to identifying the pathway along this graph, and as mentioned in Euler theorem, you must start at one odd vertex and end at the other. So let's start over here with E. We go E to D, and so E should be to A to C, C to B, B to D, D to E, A to C, and lastly C to D. Notice that we started at one odd vertex and ended at the other vertex. These are the example of Euler circuit that have degree of a vertex, since the graph corresponding to historical converge has 4 nodes of odd degree. Does not have an Eulerian path, such as what is called Eulerian circuit or an Euler tour. Such a circuit exists if and only if the graph is connected and there are no nodes of odd degree at all. Euler circuit, so when all the vertices are touching an even amount of edge, we can definitely do what the bridge of converge as proposed. However, the bridge of converge problem doesn't meet that criteria. It has a land masses or vertices touching out of edges. However, Euler found that it's still possible to create paths that don't retrace any edge while having some odd vertices. We both realized before that going through a vertex means we'll have one edge in and one edge out, right? But he also noticed that not every vertex in a graph needs to have edge going in and out. Converge problem, we were asked to hit all the land masses while crossing each bridge. This one, so what we can now define as an Euler path or Euler circuit, but since there are more than 2 vertices touching an odd amount of edge, you can say just an Euler did not. This is impossible. Absorption exercises. In exercises 1 to 4, a pen tracing puzzle is given. See if you can find a way to trace the shape without lifting your pen and without tracing over the same segment twice. If there are more than 2 odd vertices, you can. If there are exactly 2, cut start and end of those odd ones. If there are no odd vertices, if they're all even, you can start at end anywhere you'd like. In number 5, why the following pen tracing puzzle is impossible to solve. The graph of the given shape has more than 2 vertices of odd degrees, so it is not possible to draw an Euler path or Euler circuit It is not possible to trace the given shape without redrawing the same segment more than once.
Hi everyone, now I will discuss the exercise set 6.1. Number 1, transportation. And next in the table below indicate train route with corresponding cities. Draw a graph that represents this information in which each vertex represents a city and an edge connects two vertices if there is a train route between the corresponding cities. So it means, ang isang X daw na nasa table ay nagpapahiwatig ng ruta ng isang tren sa pagitan ng mga lusot. So ngayon, makikita natin sa table ang mga ruta ng tren. Kung saan simula Springfield, may dalawang biyahe ang tren papunta ng Greenfield at Mainland. At simula naman sa Riverside, may tatlo itong biyahe patungong Watertown, Mainland at New Hope. Haba ang Greenfield naman, may apat itong biyahe patungo sa Springfield, Watertown, Mainland at New Hope. At sa Watertown naman, meron lamang itong dalawang biyahe patungo sa Riverside at Greenfield. At habang ang Mainland, meron itong apat na biyahe patungo sa Springfield, Riverside, Greenfield, at New Hope. At sa panghuling biyahe naman, simula New Hope patungo sa Riverside, Greenfield, at Mainland. Number 2, transportation. The table below shows the non-stop flights offered by a small airlines. Draw a graph that represents these informations, where each vertex represents a city and an edge connects two verticals if there is a non-stop flights between the corresponding cities. Now, as we see in the table, makikita natin ang meron at walang flights. Where the Newport, wala siyang flights papuntang Lancaster and Newborn. Ang meron lamang ay ang Plymouth at Dorset. At sa Lancaster naman, wala siyang biyahe papuntang Newport at Dorset. Meron lamang itong papuntang Plymouth at Newborn. Habang sa Plymouth naman, meron lamang siyang biyahe patungong Newport, Lancaster, Newborn at Dorset. Habang sa Newborn naman, wala itong biyahe patungong Newport at meron lamang itong papuntang Lancaster, Plymouth at Dorset. Habang sa Dorset naman, wala siyang biyahe patungong Lancaster at meron lamang itong papuntang Newport, Plymouth at Newborn. Number 3, the social networks. A group of friends is represented by the graph at the left. An edge connecting two names means that the two friends have spoken to each other in the last week. So as we see, every person or a group of friends has a connection with each others. We have here the 4 questions. Number 1, or letter A, have John and Stacy talked to each other in the last week? So yes, John and Stacy have talked to each other last week. Letter B, or number 2, how many of the friends in this group has Steve talked in the last week? So, may 3 tao ang kumausap kay Steve last week at yun ay sina Michael, John, at Erin. Letter C, or number 3, among this group of friends, who has talked to the most people in the last week? The person who has talked to the most people in the last week is Michael. The local Little League baseball teams are represented by the graph at the left, an edge connecting two teams that those teams has played a game against each other in this season. So as we see, every team has connection with other teams. And there are 3 questions here. Which team has played only 1 game in this season? It is a team and the answer is it is a team of AS, Rangers, and Cubs. Letter B, which team has played the most game this season? It is the Titans, Giants, Yankees, AS, Expos, and Rangers. And letter C, last, have any times played each other twice this season? The answer is there is no time for that season.
In exercise number 4 and 5, we are going to determine whether the two graphs are equivalent. In the number 4, as you can see, it have 4 edges, the A, B, C, D, while the example number 5 has a 6 edges, the A, B, C, D, and F. So the answer is the two graphs are not equivalent because they have differences on the number of edges in the graph. Next is determine whether the graph is Eulerian. So again, Eulerian graph is also sometimes used in a weaker sense to denote a graph where every has even degree. Essentially, a graph is considered Eulerian if you can start at the vertex, traverse through every edge only once, and return to the same vertex started at. For example, let's look at the graphs below. The graphs on the left is Eulerian. You can start at any of the vertices in the perimeter with degree 4, go around the perimeter at the graph, then traverse the star in the center and return to the starting points. The graph on the right side is not Eulerian, though, as there does not exist an Eulerian trail, as you cannot start at a single vertex and return to that vertex while also traveling each edge exactly once. So, next, the cognitive bridge problem is probably one of the most notable problems. It's rather simple at hand and was taken upon the citizens of Cognitive Bridge for a solution to the question. Find a trail starting at 4 islands A, B, C, or D. The history. In Cognitive Bridge, Germany, a river ran through the city such that in its center was an island. The river broke into 2 parts. 7 bridges were built so that the people of the city could get from one part to another. The people wondered whether or not one could walk around the city in a way that could involve crossing each bridge exactly once. A crude map of the center of Cognitive Bridge might look like this. Can you find a way to cross every bridge only once? Leonard Euler created a way of looking at the problem using vertices and edges. He found that the path suggested was impossible. The diagram below shows the arrangement of a heavy trail cage for a fat hamster. Plastic tubes connect different cages. That it's impossible for a hamster to travel through every tube without going through the same tube twice. If so, find the route for a hamster to follow. Can the hamster return to its starting point without repeating any tube passages? On the right side, you can see my answer on how the hamster traveled through every tube. So, as you can see, the hamster didn't go to the same tube twice. And also, yes, the hamster can return to its starting point without repeating any tube passages.
Chapter 6, Architecture. When we say architecture, it is creating buildings, similar to as written in exercise 29 and 30. A floor plan of museum is shown. Draw a graph represent the floor plan where each vertex represent a room, and an edge connect two vertices if there are doorway of two rooms. 31. Degree of separation. An edge connect two vertices if the corresponding people have communicated by text message. Here we define the degree of separation between two individuals to be the minimum number of steps required to link one person to another through text message communication. This is equivalent to the minimum number of edge in a path connecting the corresponding vertices. Example, Karina and Luis have a degree of separation of 2. A. What is the degree of separation between Morgan and Maria? B. What is the degree of separation between Wayne and Alexander? 36. Social network.
An edge connects two vertices if the corresponding people are friends on Facebook. Degree of separation refers to the minimum number of steps required to link two individuals through Facebook friendships. A. What is the degree of separation between Brad and Marisa? B. What is the degree of separation between Sheridan and Sherna? C. List the individuals with the degree of separation of 2 from Brad. D. Do any two individuals have a degree of separation of more than 3? 33. Bridge of a graphs. An edge of a connected graph is called a bridge. If deleting the edge causes the graphs to no longer be connected, identify the bridge, if any, in each of the following graphs. 4. Travel. Draw a graph in which the vertices represent the 13 countries of South America, and two vertices are joined by an edge if the corresponding countries share a common border. B. Two friends are planning a driving tour of South America. They would like to drive across every border on the continent. It is possible to plan such a route that never crosses the same border twice. What could the route corresponds on the graph? C. Find a route the friends can follow that will start and end in Valenzuela and that crosses every border while recrossing the fewest borders possible. Hint on the graph, add multiple edge corresponding to border crossing and allow an Euler circuit.
Hello everyone, in this video, we're going to discuss graph coloring. Graph coloring is nothing but a simple way of labeling graph components, such as vertices, edges, and regions under some constraints. In a graph, no two adjacent edges or adjacent regions are colored with minimum number of colors. This number, called the chromatic number, and the graph is called a properly colored graph. Vertex coloring. Vertex coloring is an assignment of the colors to the vertices of a graph G, such that no two adjacent vertices have the same color. Simply put, no two vertices of an edge should be of the same color. A proper coloring or just coloring of a graph G is an assignment of colors, or more generally labels, to the vertices of G such adjacent vertices of colors. Consider bipartite graphs for example. If we color all vertices in one partite centroid, we will have a proper coloring of the graph. None of the red vertices will be adjacent since they all in a partite set. And similarly for the blue vertices. Furthermore, this means all adjacent vertices will belong to different partite set and thus have different colors.
Chromatic coloring. The minimum numbers of colors that a graph G can be colored with are called the chromatic number of the graph. It is denoted this is on the Greek letter pronounced. Then graph G is said to be chromatic, can be colored with the K colors certainly greater than or equal to X. Then graph G is said to be colorable.
Region coloring. Region coloring is an assignment of colors to the region of the planar graph, such that no two adjacent regions have the same color. Two regions are said to be adjacent if they have a common edge. For example, take a look at the following graph. The regions AEB and BEFC are adjacent, as there is a common edge BEA between those two regions. A region coloring is limited to an edge coloring satisfying the cycle condition. And the dual construction builds a region coloring from any color cycle and any embedding of the graph. Similarly, the other regions are also colored based on the adjacency. This graph is colored as follows: blue, red, blue, and blue. The complete graph, each vertex is adjacent to remaining and vertices. Hence, each vertex requires a new color. Hence, the chromatic number of Kn is equals to n.
Application of graph coloring. Graph coloring is the one of the most important concept in the graph theory. It is used in the many real-time application of computer science such as clustering, data mining, image capturing, image imitation, networking, resource allocation, process, and scheduling.